Okay, good morning everyone. Welcome to week 5 of your stats class. If you haven't already, you might want to print out slide 4 of this presentation. We're going to go through, it's sort of a flow chart of how to choose which stat to use, and it might be helpful to fill it out as we go. If you don't have it printed out, not a big deal either. As always, this session will be recorded. Okay. So the first two things we're going to go through today are more of FYIs than anything else. You will never have to actually conduct the test I'm about to talk about, but as you start reading different research, you will read about the tests that I'm going to start talking about. I know ANOVAs and the next thing chi-squares in either the Page article or the Caldwell article. You've already seen them. So I thought it's a good idea to spend some time talking about what these two tests actually mean. So, ANOVAs is like a t-test, but whereas a t-test only compares, I forgot. Anybody have any questions before we go on to this week's content? Anybody have any questions from anything going in the past? Okay, so like I said, ANOVAs are like t-tests. They're looking to see whether two or more samples and whether the differences in those samples are significant. So a t-test is where you take two sets of variables and you have the t-test, you compare and say, okay, the post-test was significantly higher than the pre-test. Great. And we've talked about how every time you run an t-test, we are willing to accept a certain amount of error. And that's that p is less than 0.05 or p is less than 0.01. So, when we run a t-test, we are willing to accept that error. And generally in education, we're willing to accept about a 5% margin of error every time we run a t-test. Well, think about if you were running multiple t-tests. Every time you run one of those t-tests, you are introducing a 5% margin of error. And again, and again, and again, every time you run it. Well, an ANOVA, what it does is it runs multiple t-tests at one time so that there's only one error. Instead of compounding the error over and over again, you're just going to run multiple t-tests at the same time. So for example, let's say you were doing a research study on tomatoes in your backyard. And you want to see which tomatoes, plants, and which fertilizers work best. So you might buy some plants from Home Depot, you might buy some plants from Lowe's. And then you're going to try fertilizer A and fertilizer B. Well, what an ANOVA would do is it's going to look at all at one time. It'll run a t-test between which plants are best, Home Depot or Stein. It'll look at the fertilizers and tell you if there's a significant difference between fertilizers. And then it's also going to look at all the combinations. It'll look at fertilizer A with Home Depot, fertilizer A with Stein's, fertilizer B with Home Depot, fertilizer B with Stein's. All the different combinations you can get with the two different types of fertilizers and the two different types of tomatoes. It'll run multiple t-tests all at once and tell you whether or not there's a significant difference between all of those different things. Like I said, you're never going to actually conduct an ANOVA on your own, but you will be reading about them. So, based on that, anybody have any questions? Okay. The other test that, again, is just going to be an FYI for you is going to be a chi-square. And if you read the description, it sounds similar to a t-test. You know, whether there's a significant difference between the observed frequency and the expected frequencies. Now, in an improper way of saying it, a chi-square is like a t-test for nominal data. So if you're going to have a survey, you'd be using a chi-square to see if there's a significant difference between what, let's say a pre-survey and a post-survey. And here's, in a nutshell, how it works. Imagine a coin toss. Now, if you were going to toss a coin 100 times, one would expect there to be about 50 heads and 50 tails. But we know from experience that it doesn't always work out that way. We might have 51 heads, 49 tails. We might have 55 heads, 45 tails. Or we might have 60 tails and 40 heads. It's never going to come out to be exactly 50-50. What a chi-square does then is it looks to see if there's a significant difference between what we observe, our actual tosses, and what's expected, the 50-50 mix. And it's going to look at those and say, okay, 45 heads, 55 tails, probably not a significant difference. So we still consider that a fair coin. But if there was a 70 heads and 30 tails, we would say, that looks like to be a significant difference from what we actually got, from what we expected. So this might not be a fair coin. Well, what the mathematician geniuses have figured out is how to do that with all sorts of data. So when you take your surveys and you have the I really liked versus I really hated type of surveys, you are able to run chi-squares on those to determine if there is a significant difference between the pre-surveys and the post-surveys. Again, this is not something that you're actually going to run, but it is something that I want you to be aware of, because as you read research, you will be reading about this. Questions? Okay, so choosing a statistical test. As you go forward in your research, you are going to need to figure out what type of statistic you can use to figure out what you want it is to know. Now, this flowchart here can help you to do that. And that is what we're going to start going through now. So, in these first three boxes, we are working off of scales of measurement. So, what are the 4 different scales of measurement? Okay, perfect. We got a couple answers. So yeah, the first one we're going to work out with is nominal. And if you remember, nominal is like name data. That would be your social security numbers, jersey numbers. Heck, a telephone number could be a nominal data as well. When you have a number that represents a person or a thing, that is going to be nominal data. Our second one was going to be ordinal data. That's where you put things in order, first, second, third. And then in this last box, we're going to put interval/ratio data. For the purposes of our course, the statistics that we use all treat both those types of data the same way. Okay, so let's look at the flow chart. We got scales of measurement, nominal data. Throughout this entire course, we have only studied one type of statistic that can be used with nominal data. And what it does is it tests the difference between two sets of data. What goes here then? What do we use that can nominal data that looks for differences? In the extremely recent past. No, t-tests need to work with interval or ratio data, but they do look at differences. Exactly. The chi-square is what we have, so a little bit tricky since we just talked about it. But yeah, so if you were working with nominal data looking for differences, you would use the chi-square. Okay. So ordinal data, and we are looking at relationships. What would we use to find the relationships in ordinal data? Okay, perfect. Between Kurt and Sarah, we got a Spearman correlation. Whenever you're answering questions via, there's going to be eventually a group final and an individual final, make sure that you are specific. You would not just say Spearman, you would have to say, and you would not just say correlation. You would need to actually say Spearman correlation. So the more specific, the better, so that we really are clear about what you guys are talking about. Spearman, oopsie, correlation. Perfect. Okay, so here we have interval ratio data. We have another hypothesis, which is relationships. So what would go here? Perfect. So over here we've got the Pearson correlation. Okay, now we're still in interval ratio data. Now we're looking at a hypothesis for differences. What would go over here? We have interval ratio differences with a pre-post test, one group. Okay, perfect. It is a t-test. What type of t-test? Perfect. A dependent t-test. Now, we also talked about so dependent is when you have a pre-post test. We'd also talked in the past about one-tailed or two-tailed. Now, that really doesn't fit well into this flow chart. But if you remember, a one-tailed t-test is when the researcher specifies which direction the data is going to go. If the researcher thinks the data is going to go up, or if the researcher thinks the data is going to go down. Both of those would be a dependent t-test. I'm sorry, a one-tailed t-test, because the researcher specifies which direction it's going to go. If the researcher is just looking for any old difference, then it would be a two-tailed t-test. Okay, so interval ratio data, hypothesis difference. Now we have two groups. What would go here? Okay, perfect. Independent t-test. Okay, and it's independent because we're going to have two groups, which means we're going to have our control experimental group, and we'll see if there's a difference between. Okay, so if we have more than two groups, we're still in interval ratio data, we're still looking at differences, but now we have more than two groups. What would we use for that one? Okay, Valerie's on the ball. Yep, perfect. So, looking just at what we talked about today, that would be the ANOVA. Now, this summarizes our course in all but one thing. What have we talked about in this course that did not make it onto this flow chart? Right, all of the descriptive stats, such as standard deviation, mean, median, those aren't on there either. But there's another statistic where we did a lot of work with it more. Think about when you're starting to compare groups or compare people to themselves, compare people to their peers. Perfect. So the curve works in conjunction with the z-scores. So the test width that I'm looking for is a z-score. Do not forget about those. The z-scores are used, again, if you have two separate groups or two different types of tests and you want to see how one person did relative to the group, how they did relative to themselves on different tests, that is going to be the z-score. It allows you to compare these two different things. Okay, so what we're going to do now is take a few examples, and we're going to figure out what statistic we would use. And again, I'd urge you to please be as specific as possible. You would not say t-test, you would say one-tailed dependent t-test. You would not say correlation, you would say Spearman correlation. So, looking through this, you're a third grade teacher. You want to pre-test them, group them according to ability, post-test them. How would you see if grouping made a difference? What would you use? Okay, very nice. Okay, so we're all in agreement that it would be a dependent t-test. We know it's a t-test because we're looking for a difference. We know it's a dependent t-test because it is a post-test and a pre-test. Now, there's disagreement on whether it's a one-tailed or a two-tailed t-test. And based on this description, you really wouldn't be able to tell conclusively, because it doesn't say what the researcher is looking for. Oh, it does. My mistake. It says right here, see if grouping made a difference. Because it says made a difference, not a positive difference, did not say whether grouping made the scores go up, it's saying whether it made a difference. And that's your clue word right there. Because it's just looking for a difference, it's a two-tailed dependent t-test. We have a few of these examples. Questions on this one? Okay. Random survey was taken to see if the number of hours work was related to a student's GPA. What statistics would you use? Okay, nice. Pearson correlation. We know it's a correlation because we were looking for related. And we know it's a Pearson correlation because both GPA and the number of hours worked are in interval/ratio data. Nothing is in ordinal. Any questions on that? Okay. New method of reading. You want to look for an improvement to see if the new method produced an improvement in score. You collect data to the unit and then again after the unit. What would you see if the achievement was positively affected? Okay, very nice. So we know it's one tail because it's looking for positively affected. Also, we know that from improvement. We know it's dependent because they are pre-testing and post-testing. And we are looking at a t-test because we're looking at whether it affected the achievement, not to see if there's a relationship between the two. So it is for sure a one-tailed dependent t-test. Nice. 200 students randomly chosen to determine if a relationship exists between achievement and social rank. What are you going to use? Nice. Okay, good. Spearman correlation. We know that. We know it's a correlation because we're looking for a relationship. We know it's a Spearman because here we have social rank. It's going to be rank order, not some test on socialness. It's how they are ranked. So it's going to be Spearman correlation. And remember, if you're going to plug this into Excel, you would need to convert their achievement, whatever they're going to use for achievement, whether it's their GPA, ACT scores, some random Spanish test that they took, convert that into ordinal data first, and then correlate that with their social rank. Okay, fifth grader has been having difficulty in two areas, math and reading. You administer tests in both areas and compare the student to himself. What information would you need to do this? What statistic would you use? Let's start with what statistic would you use? Okay, nice. So you would use a z-score. Okay, and as far as the information, I see Kurt's got that. So when you're looking at information, what information do we need? Well, we're going to need the mean, the standard student score, and the standard deviation. Yes, we're going to need that for both tests. So for the math test, we need the mean score for the class, the student score, and then the standard deviation for both, for the class. And same for the reading. We would need the mean, the student score, and the standard deviation. Okay, so we would calculate, we would take those, and again, if you forgot, it would be the mean, the student score minus the mean divided by the standard deviation is going to give you the z-score. And when I was grading the standard score project, some of you were getting a little bit confused on that. The score that you calculate by doing that formula of mean minus, student score minus the mean divided by standard deviation, that gives you the z-score. Let me write that out. Z equals student score divided by the mean, nope, it doesn't, minus the mean divided by the standard deviation. That is the z-score. And that is a score that then you would take that z-score, you would have your number line, you would draw your curve up on top of it, and you would plug the z-score somewhere on the curve. So if that's our 0 point, that's our 0 point, and then you would put your z-score somewhere here. And then when you put that z-score on there, then you are going to take that z-score and find the z-score on the chart to calculate the area under the curve. And remember, the chart that I linked up calculates the area from your z-score to the mean. It is this area right here. And then you're able to take that and other knowledge you have and calculate how many percent of students scored above or below your student. So the number that you get from the calculation, that is the z-score. The number you get off the chart is the area underneath the curve. Any questions on that? Okay. Any questions on anything before I move on? Because we're going to switch gears in a second. Okay, onward then. So this was the last live lecture of your class. Next week, I'm not going to be lecturing. The 8 to 9 o'clock hour is going to be more just open office hours. You are welcome to come and just hang out and see if anybody has any questions and listen to their questions. You're welcome to pop in, ask your question, and then leave. Totally up to you how you want to use that time, but there is going to be no live lecture next week. Most likely I'm not going to record the lecture either, so don't plan on seeing anything linked up in Canvas. It's just an open office hour to get together and ask questions. So, because there is no class for next week, I wanted to preview what you're going to have to worry about next week. So, in week 6, there's going to be only one README file. And there is no Part A, Part B. It's a short, very condensed. And you are going to have to complete the individual portion of the final. This is done on your own. It is going to be due on August 12th. And please pay close attention to the directions for Section 1. Sometimes people don't, and then they get themselves in a little bit of trouble. So really read the directions closely for Section 1. As far as this week's information. So, due today, you have your group project due for a research report due to. That is your descriptive project on the Caldwell article. You have your correlation project due today. Also, that's your individual project. please make sure that you get them in. I've had some people who have been getting a little bit lackadaisical with the work, so make sure that you are in there by the end of the time, by the due date. Benchmark number 4 is due on August 5th. Most of it is self-graded. I will look through the parts that aren't once everybody has it submitted on Friday night. Next week, Monday, you have your inferential project due. Now remember, that's a group project where you are going to be inserting the inferential stats, the t-tests, into the descriptor project you have already completed. I have reviewed and graded all the descriptor projects already, so remember, please make any necessary changes to your descriptor project prior to changing it into an inferential project. Make sure it's all cleaned up, everything's perfect from the descriptive side, and then add your inferential stats. And just to be clear, what you're going to be doing is adding the t-tests to each of your tables, so that's on there. You're not going to be putting t-test results onto a graph because it wouldn't make sense. And you're going to be adding one line to each of your paragraphs, so 6 sentences for each of your paragraphs saying, yes, there was a significant difference, no, there wasn't a significant difference, at p is equal to or less than 0.05. And then you're also going to need to modify your summary. Perhaps, even though all of you guys said the teachers should be happy, maybe after running the t-test you find out that none of them had a significant difference. And if none of them had a significant difference, then what the teachers didn't really do anything, in which case they should not be happy. Or perhaps after running the t-test you find that all of them were significant, and your conclusion that the researcher should be happy was correct. But you'll need to modify that summary paragraph with the information found from your t-test. Also assigned today, there is a group culminating project that is due next week, Monday. It's a group final. So read through all that, get the information in, submit it via Canvas, and you should be good to go. Does anybody have any questions on any of the assignments or anything in general? Anything that you needed to talk about? Okay, if you guys don't have anything, that is all I have for you today. Have a great rest of the week. Remember, as we're getting down to crunch time now, please contact me quickly if you have any questions or concerns about the class. We've got 2 weeks left and you will be done. Have a great rest of the day and a great rest of the week.